Welcome to section 7.5, Logarithmic Functions. At the end of this section, you should be able to answer these questions. What is the general equation of a logarithmic function? What is the relationship between a logarithmic function and an exponential function? What are the key characteristics of a logarithmic graph? What is the numerical pattern associated with logarithmic functions? And finally, how do we solve for a particular logarithmic function given data or a graph? Well, let's start with the general equation. Here, the general equation of a logarithmic function in its untranslated form is y equals a plus b log base c of x. A, b, and c are constants. B can't be equal to 0, because then you would just have y equals a. C has to be greater than 0. To raise something to a power over particular values of x, we need to use positive bases. C can't be equal to 1. A base of 1 would result in a constant value of y equals 1. If we are going to transform the function, then our equation looks like this. Y equals a plus b log base c of x minus d. A is going to be our vertical translation. B is our vertical dilation. And d is the horizontal translation. Here I've graphed 5 different logarithmic functions. Log base 2 of x, log base 3 of x, log base 4 of x, log base 5 of x, and y equals log x, or base 10 of x. Let's look at the different graphs and figure out how we can determine which of the graphs is associated with which of these equations. Alright, first of all, let's look at and notice that each of these graphs has certain characteristics in common. First of all, they're all increasing as long as x is greater than 0 and have no values for x less than or equal to 0. And finally, they all go through the same point here. They all go through 1, 0. Now let's look at how they differ. You'll notice that if I look at each of these possible graphs, for instance, y equals log base 2 of x, I can rewrite this as an exponential function. So 2 to the y equals x. And if I want to know what happens when y equals 1, 2 to the first is going to be 2. So when x is 2, we are going through y equals 1. If my graph is y equals log base 2 of x. If my graph is y equals log base 3 of x, well, log base 3 of 3 is equal to 1, because 3 to the first power is going to result in 3. So log base 3 of x has the point 3, 1, which means that log base 4 of x should have the point 4, 1, and log base 5 should have the point 5, 1, and log base 10 should have the point 10, 1. So if I look at these different graphs, I can see that at 2, 1, that's my green graph, which would mean that log base 2 is the green graph. The graph that goes through the point 3, 1 is this purple one. So log base 3 of x is going to be the purple. And we can see that the graph that goes through 4, 1 is the blue. And the orange goes through 5, 1, so that's log base 5. And finally, the one that goes through 10, 1 is log x. Let's look at what happens when we determine the inverse of the natural log function. If I start with the equation y equals log of x. So let's use the common log function. And I'm trying to determine the inverse. So this is f. So the inverse of f would, the first thing we would do is switch our x's and y's. So x equals the log of y. Now, if I burp that equation, solve for y, then in my inverse, y is equal to base 10 to the x. So if my original equation is a logarithm, the inverse of that equation is an exponential equation. Logarithms are inverses of exponential equations and vice versa. Alright, so let's see what we can do with these logarithms. First of all, we've just looked at the patterns for linear equations, power functions, exponential functions, and quadratic. Since we now know that logarithms are inverses of exponential equations, and we know that exponential equations have an add multiply what do you think multiply the pattern will be for a logarithmic equation? Alright, well, I hope you guessed that since exponential is add multiply, logarithms will be multiply add. Here's an example of some data points from a logarithmic function. If I look at my pattern, here I'm going to be multiplying by 3 each time. And the result is I increase by 1 each time for my y values. Now,